Good morning. Today we are going to see harmonic functions, conjugate harmonic functions, theorems, results, and the proof for this. A real valued function of two variables x and y is said to be harmonic if the second order partial derivatives exist and they are continuous, and it should satisfy Laplace equation. Conjugate harmonic function: if f of z, which is equal to u plus iv, is an analytic function of z, then v is called a conjugate harmonic function of u, or otherwise u is called the conjugate harmonic function of v. Next we are going to see properties of analytic functions. Property 1. The real and imaginary parts of an analytic function f of z equal to u plus iv satisfy the Laplace equation. That is, we are going to prove u satisfy Laplace equation, v satisfy Laplace equation. So we can call their harmonic functions. Proof: f of z is u plus iv is an analytic function. If it is an analytic function, the first order partial derivatives exist, they are continuous, and they satisfy CR equations. I am taking the first equation, it's equation 1, and the second one is equation number 2. Next, we are going to prove that it is harmonic, u is harmonic. So if you want to prove u is harmonic, I have to prove it satisfies Laplace equation. So I require second order partial derivative of u with respect to x and second order partial derivative of u with respect to y. So first equation I am going to differentiate partially with respect to x. Second equation I am going to differentiate partially with respect to y. This is equation 1, partially differentiating with respect to x, we get uxx. And the second equation, partially differentiating with respect to y, will get uyy. And adding these two equations 3 and 4, uxx plus uyy will be vyx minus vxy. And that is equal to 0 since vyx is equal to vxy. So therefore u satisfies Laplace equation, hence I can prove that u is harmonic. Similarly, I should prove v is harmonic, so I have to prove that v satisfies Laplace equation. So the first CR equation I am differentiating with respect to y and to get vyy, and second CR equation I am differentiating with respect to x to get vxx. And adding these two equations, taking this minus sign to the other side, I'll get a vxx plus vyy is equal to uxy minus uyx, and that is equal to 0 since they are equal. V satisfies Laplace equation, hence I can say that v is harmonic function. Thus u and v are harmonic functions. Converse of the above result need not be true, and the example for this I have given in the notes already. Next, so we saw how to prove that the real and imaginary part of an analytic function satisfies Laplace equation in Cartesian form. Now the statement here it is given in polar form, and you have to try this proof. You have to try and prove that u satisfies Laplace equation, v satisfy Laplace equation in polar form. And the notes already given to you, the proof is already there with you, so you can go through that, it will be clear for you. Hello everyone, we are going to see how to construct the analytic function using Milne Thomson method. To find the analytic function, if the real part is given, imaginary part is given, that is listed down. So if real part, that is u of x comma y, is given, then f of z can be found by using integration dou u by dou x at the point z comma 0 minus I times integration dou u by dou y at the point z comma 0. Using this, we can find what is the analytic function if the real part of the analytic function is given, that is u is given. If v is given, that is the imaginary part of the analytic function is given, then f of z can be found by integration vy at the point z comma 0 dz plus I times integration vx at the point z comma 0 dz. Next way of finding analytic function is If the real part is given, then we can find the imaginary part v by using another method, and then substituting what is u and v here, we can find what is the analytic function. That is another way of constructing the analytic function. So for example, u is given, here u is given, and if you want to find out what is v, we need to start with the total differential coefficient of v. That is, we need to write dv as dou v by dou x into dx plus dou v by dou y into dy. Then this dou v by dou x and dou v by dou y we can rewrite using this Cauchy-Riemann equation. As the function is given as analytic function, then that CR equation will get satisfied. So applying CR equation, we can write Vx as minus uy and vy as ux. So after rewriting like this, we can substitute the partial derivative of u with respect to x and the partial derivative of u with respect to y in this. Then knowing what is dv, upon integrating, we can get what is v. So this is how we can find what is the function v, which is otherwise called as conjugate harmonic function. So if we know what is u and v, substituting here, we can get what is the analytic function. With the example, we will see both the methods, how to find out the analytic function if u is given, that is real part of the analytic function is given. So see this example, here u is given as x square plus y square. We need to find what is v, and then we need to find what is f of z. So first we need to find what is v, which is called as the conjugate harmonic function, right? So for that we require what is the partial derivative of u with respect to x and partial derivative of u with respect to y. So if you differentiate u with respect to x, you will get 2x. Differentiate u with respect to y, you will get minus 2y. Then we need to take the total differential coefficient of v. Then using this statement, we can get what is dv. So for that we need to rewrite the dou v by dou x first in terms of u, dou v by dou y in terms of u's. So by CR equation, I can write ux equal to vy and uy equal to minus vx. So we can substitute vy as ux and vx as minus uy in this. So derivative of u with respect to y is available here, it is minus 2y. So minus of minus 2y, it will become plus 2y here. And here we need to substitute what is ux. So ux is 2x. Then you can take this 2 outside, which is common, and you can rewrite the previous statement as x dx plus y dy. So this x dx plus y dy statement, we can rewrite it as derivative of xy. So what is derivative of xy? X into dy plus y into dx. So it is based upon product rule. So integrating this statement dv, we will get what is v. So v is equal to integration 2 times derivative of xy, which is 2 times xy plus the integration constant c. So substituting this v and the given u, we can find what is the function f of z. F of z equal to u plus iv. So now I need to rewrite this statement as x square plus 2x, and this I and y I am combining and writing as iy. Then minus y square is there, that I am rewriting it as I square y square. I square is minus 1, so that it will satisfy with this minus sign. So now it is of the form a square plus 2ab plus b square, that I can write it as a plus b the whole square. So I am getting it as x plus iy the whole square. X plus iy can be written as z. So I am getting z square plus the integration constant c. So the function f of z equal to z square. So this is how we can find what is the analytic function by finding what is v if u is given. Then the same example we can take, and by applying Milne Thomson method, we can find directly what is f of z. So we'll check whether we are getting the same answer. So same example I'm taking here, then I'm going to apply this Milne Thomson method. So first I'm getting what is ux and uy. Then I need to find what is ux at the point z comma 0. Then I need to find what is uy at the point z comma 0. So substitute x as z, y as 0. So this will become 2z, and here if I substitute y as 0, it will become 0. Then by Milne Thomson method, f of z equal to integration ux at the point z comma 0 dz, and there is a minus sign, I times integration uy at the point z comma 0 dz. So if I substitute what is ux at the point z comma 0 here, it will become 2z dz here, and here uy at the point z comma 0 0. So this integrand becomes 0. So therefore if I integrate this 2z with respect to z, I'll get z square. So same answer we are getting here. So by Milne Thomson method, we can construct the analytic function f of z. Otherwise, by finding the conjugate harmonic function also, we can find what is the analytic function. Then we can say one more example to make this clear. Another example I'm taking here is sin x cos hy, u is given. So we need to first show that this is harmonic function in this. Then after that we need to find the harmonic conjugate. Then we need to find the analytic function. So first I am going to show you how to check whether the function is harmonic. So how can we check whether the function is harmonic function or not means, already we saw in the previous video that second order partial derivatives should exist, and it should be continuous, and it should satisfy Laplace equation. It should satisfy Laplace equation. So we need to first get the partial derivatives, second order partial derivatives. So take u sin x cos hy, partially differentiate with respect to x. So derivative of sin x is cos x. Retain this cos hy as it is. Then derivative of u with respect to y, partially retaining sin x. So derivative of cos hy is sin hy. Then again I need to differentiate this ux with respect to x partially, so that I will get uxx equal to minus sin x cos hy uyy, means we need to differentiate uy partially with respect to y. So partially differentiating the sin hy will get cos hy. So then we need to check whether uxx plus uyy equal to 0. Adding this, we are getting it is equal to 0. So therefore it satisfies the Laplace equation. Hence we conclude that u is a harmonic function. Then after concluding u is harmonic function, next we need to find what is the harmonic conjugate and then the analytic function. How to get the harmonic conjugate, that is we need to take dv first. dv is dou v by dou x dx plus dou v by dou y dy. Then we need to rewrite this dou v by dou x and this dou v by dou y using CR equations. So after rewriting that in terms of u's, we need to substitute what is ux and uy. Then we need to integrate this by combining the terms. So after substituting, we need to combine these two terms and rewrite it. So now we are having minus sin x sin hy dx plus cos x cos hy dy. So that together we can write it as derivative of cos x cos hy. So derivative of cos x cos hy, derivative of uv is uv dash plus vu dash. So similarly we can get cos x cos hy dy. Then retaining this sin hy, derivative of cos x is minus sin x dx. So we'll get back this term. So this term together I can write it as derivative of cos x sin hy. If I integrate this, this derivative integration is reciprocally related, so it will get cancelled. So therefore v is equal to cos x sin hy. Then after getting this conjugate harmonic v, we can construct what is f of z by u plus iv. So substitute the given u and substitute what is v, just now we found it. Then we need to simplify this and we should get the function of z. So sin x cos hy is a. This hyperbolic function we need to rewrite it as circular function, and then the sin hy we need to rewrite it in terms of circular function. So already I gave this to you. Cos of ix can be rewritten as cos hx, and the sin of ix is equal to I times sin hx. This is the relation between hyperbolic function and circular function. So I can rewrite cos hy as cos of iy and the sin hy as sin iy divided by I. So this I will get cancelled with this, remaining it is sin x cos of iy plus cos x sin of iy. It is of the form sin A cos B plus cos A sin B. So that is equal to sin of A plus B. So that can be rewritten as sin of x plus iy. X plus iy is z, so therefore we are getting f of z as sin z. This is one way of finding what is f of z by finding conjugate harmonic function. Then the other way of finding what is f of z is by using Milne Thomson method. We can find directly what is f of z. That you can try. Then next, so the two examples we saw that u is given how to find the analytic function. In this problem v is given and then using Milne Thomson method we are going to construct the analytic function f of z. So here v is given. First we need to find what is the partial derivative of v with respect to x and with respect to y. So this exponential term has been rewritten in terms of hyperbolic function sin hy because we can rewrite e power y minus e power minus y as 2 times sin hy. So after rewriting, if you are going for differentiation, it will be easy. So differentiate this partially with respect to x, partially with respect to y. Then find what is vx at the point z comma 0, vy at the point z comma 0. Then apply Milne Thomson method, f of z equal to integration vy at the point z comma 0, then plus I times integration vx at the point z comma 0. So substitute what is vy and vx here, so that x is 0. So this integrand will become 0. This term will become 0. And remaining, if you integrate with respect to z, we'll get it as integration of sin z is minus cos z. So altogether we'll get it as 4 cos z. So this is how we can construct the analytic function by applying Milne Thomson method.